In this chapter, we are going to return to regression, which we first studied in chapter 3. So before you start this unit, it might be useful to just take a look at your chapter 3 notes and remind yourself what regression was all about. So we're going to do that in this lesson as well, but if you find yourself getting stuck or needing to go back and reference other stuff, chapter 3 is the place to look. So recall that a regression model describes the relationship between a quantitative response variable, which is the y variable. Some books call that response variable, actually most books call that response variable the dependent variable. And one or more explanatory variables, which is the x variable. Most books call that the independent variable. And because regression models can be used to make predictions, sometimes the x variables are called the predictors. So you can do regression and make things that are not straight lines, but that's not this class. That's a different class called Stat 401. But in this class, we're talking just about straight up linear regression. And a regression line is something of the form y hat equals b naught plus b1x. And y hat is the predicted or estimated mean for a specific y value. So for example, like if this equation, we have x equals, height in inches and y equals weight in pounds, y hat would equal what you think someone's weight will be based on their height. And there is variability. People that are the same heights weigh different things. So this y hat is giving you the average weight at a specific height. And another good question to ask is, well, how much people vary around that average? And we'll talk about stuff like that in this lesson. Remember that B0, which is this thing is read B naught, is the y-intercept of the line. This is the value of y hat when x equals 0. You can verify that. Plug in 0 for x. Y hat is b naught plus b1 times 0, which is the same thing as b0. b1 is the slope of the straight line. You can see that you've got kind of a b plus mx form if you think back to like algebra 1. The slope tells us how much an increase or decrease for y hat when x is increased by 1 unit. We talked a lot about how to interpret the slopes of these lines. Remember, it's change in y over change in x. So to find the units of the regression line, you look at y's units over x's units. And a residual is used to describe the deviation of an observed y and the value of y hat, or the predicted y. It is computed as observed minus predicted, which is the same thing as y minus y hat. So quick review. Suppose that medical researchers use sample data to find a regression line describing the relationship between systolic blood pressure and age for men between the ages of 40 and 60. And the simple regression line is given by estimated mean blood pressure is 85 plus 0.9 times age. So in other words, I'll probably write that instead as y hat equals 85 plus 0.9x, just because it's way easier than writing down the words. Okay, so give the value of the slope and write a sentence that interprets it in the context of the situation. So the slope is 0.9. And because that slope is positive, this means that blood pressure increases with age. And that is true on average. It's not true that for every single person their blood pressure goes up as you get older. You can make lifestyle changes that causes it to go down. But for the average person, if you look at lots of people as a group, the blood pressure does tend to go up. Okay, now let's think about what the units here are. We have change in y over change in x. Now y is blood pressure and x is age. And so we know that since the slope is 0.9, for every 1 year increase in age, that's like saying the denominator changes by 1. Like think about this as 0.9 over 1. Blood pressure increases 0.9, and I forgot to tell you what the units were, so we'll just say units, which I think is like millimeters of mercury or something, but I'm afraid I'm a math teacher, not a nurse, so I don't know. Bonus to you if you're in the medical field and you can say what that should be. But the kicker is that as x goes up by 1, this is how much y goes up by. Estimate the mean systolic blood pressure of men who are 50 years old. So plug in 50. Y hat is 85 plus 0.9 times 50. And so you get that y hat is 130. And I think this is millimeters of mercury, so we'll just go with that for now. So what this means is that an average 50-year-old man has a systolic blood pressure of 130 millimeters of mercury. And that doesn't mean that every single one does, just that the average 50-year-old man, this is what you would expect to see. Suppose that the systolic blood pressure of a 50-year-old man is 125. What is the value of the residual for this man? Well, recall that the residual is equal to y minus y hat. And y is the actual value, which in our case is 125. Y hat we found in part B, that was 130. So the residual is negative 5 millimeters of mercury. And then explain in words what the residual you found in part C indicates about the relationship between the systolic blood pressure for that person and the estimated mean systolic blood pressure for the 50-year-old man. So the person in part C, his blood pressure was lower than the average. And you can tell that based on two things. Either 125 is smaller than 130, that's easy enough, or you get out a negative answer from your residual. Either way, both of them are pretty easy. So the person in part C has a systolic blood pressure that is 5 millimeters of mercury below the average. Now, to be consistent with using Greek letters for population parameters, like think back we used mu for the mean. So the regression equation, as in the true regression equation, is given by this formula, and that's called the expected value. And this expected value, really remember back from chapter 8, that's a mean. So it's what you'd expect to see on average for this, like this person with characteristic X. And note that y hat is an estimate of this expected value of y. So y hat is found from data, and it estimates this true regression line, kind of like you used x bar to estimate mu, or you used p hat to estimate p. It's just here the regression is a little bit more complicated. Like finding that y hat regression line is really tedious and often use a computer. B0 is the intercept of the true straight line in the population. It's estimated by B sub 0. So this is actually a beta. Beta 1 is the true slope of the straight line in the population, and it's estimated by B1. So that's about equal to, or estimated by, y hat equals b naught plus b1x. And this is from data, and this is the true line that you could find if you could possibly ask everybody and use all that data, but that's pretty much impossible, so or expensive and time consuming, so you're forced to do estimations. So next example, heights and answers to the question, how much would you like to weigh, were recorded for 126 women in a statistics class. The regression equation for y equals desired weight in pounds and x equals height in inches is given by this equation. So what is the slope of the regression line, and write a sentence that explains what it means. So m is equal to 2.90. And think change in y over change in x. So y's units is the desired weight. Which is measured in pounds. Over x's units, which is the height in inches. So think about that as 2.9 over 1. So if height, that's x, increases by 1 inch, desired weight increases by 2.9 pounds. I mean, people who are taller understand they cannot weigh as little as people who are shorter. So this is just saying that if you look at someone who's, 5'6" versus 5'7", the person who's 5'7", their ideal weight will be on average 2.9 pounds more than the person who's 5'6". Assume these women represent all college women. What is the proper notation for the slope? As in, is it beta 1 or is it B1? And explain. Well, even though they represent all college women, this is data from a sample. So the regression line was found from a sample. Found from sample data, not the entire population. And because it's a sample and not everybody, it's not the true value, it's only an estimate of true value. So the proper notation is B1. What is the estimated mean desired weight for women who are 65 inches tall? Just for your reference, that's 5'5". So, well, the estimated mean desired weight of people that are this tall, 65.4 plus 2.90 times 65, turns out to be 123.1 pounds. So on average, women who are 65 inches tall, desire a weight of 123.1 pounds. Now, when talking about regression, we make a couple assumptions about how this regression line works. And one of them is that you assume constant variance. And this means that the size of the deviation of the y values from the line is about the same for all the x values. So in a picture, suppose you have your regression line, and then you have your data. And what this says is that that spread around the line is about the same no matter where your x is. Meaning that this spread here is the same as that spread there, which is the same as that spread there, same as that spread there. So that's one assumption that you do make here, is that the spread is the same. And then you also assume that for each specific value of x, the distribution of the y values is normal. So once again, you have your regression line and you have this, spread around it. And what you kind of assume is that for each of those, there's going to be this sort of normal curve there around the line. So, sorry, bad normal drawing. But that most of the people are going to fall close to the line, and then some of them will fall far away. So think about this in terms of, say, this x is equal to height, and y hat is equal to weight. And you're predicting weight based on height. Suppose your given height is 65 inches. Lots of people are going to be this average weight, and there'll be some variation around that average weight. So those are two assumptions for looking at regression lines. Constant variance, and for every specific x, the distribution is normal. For a regression model, the standard deviation measures roughly the average deviation of the y values from the mean, or in this case, the mean is the regression line. So the standard deviation is measuring that constant spread. And that's definitely one thing you should get out of this class, that standard deviation is a measure of spread, how much variability there is in a set of data. So in this case, the standard deviation, you're almost never going to have to find it, but here's what the formula is. You first find the sum of squared errors, which are the squared differences between the observed and predicted values. In other words, the residuals. Or the residuals. This is called the SSE, for sum of square errors. And then you find the standard deviation like this. So take the sum of squared residuals divided by n minus 2, take the square root. I made a teensy bitty mistake here. I forgot to put a squared sign there. But what this says you do is take your observed minus predicted squared for every single data point, for all data points, and then take a sum. That's what this numerator means. Add them all up. But this is really usually quite tedious, as you saw in maybe a previous lesson where you were forced to find standard deviation either by hand or using a computer. So pretty much always I'm just going to give this to you, but this is where that formula comes from, or where the number you're going to get comes from. Okay, previously in chapter 3, we learned that the squared correlation R squared measures how well the explanatory variable explains the variation in the response. And the statistic is also denoted by capital R squared, and the value is commonly expressed as a percentage. Researchers typically use the phrase proportion of variation explained by X in conjunction with that value of r squared. And here is the formula. R squared is given by this thing called SSTO minus SSE over SSTO, which after some algebra gives you this thing. Statisticians love these shortcut names, and so it's just good you kind of have seen them before in case you take another statistics class. So in this formula, SSTO is called the sum of square differences between the observed y values and the sample mean. What this stands for is sum of squares total. And it's found by doing the sum of your observations minus your mean and squaring. That is what SSTO is. Remember that SSE stands for sum of square errors, and this is found by taking the sum of the y sub I minus y sub I hat squared. And then lastly, SSR is the sum of the squares explained by the regression, and this is found, so that stands for sum of squares regression. And it turns out that that is the sum of yi hat minus y bar squared. Now you won't have to do these things on a test. Maybe your take-home quiz, but not an in-class test. But you might have to use them if you take a future statistics class, so it's good to have known sort of what they stand for. And you can prove using algebra that when you take this expression minus this expression, you end up getting this expression. But that's tricky, tedious algebra, so we're not going to do that in this class. You might have to do it in a later class if you take more statistics. The temperature data set on the companion website gives us the mean April temperature in Fahrenheit and geographical latitude for 20 US cities. And if you take that data and you ask a statistical software to fit a regression line to it, you get this. Y hat is 119 minus 1.64x. So what this will tell us, because the slope is negative, just first to point that out, as latitude increases, temperature decreases. That should make sense to everyone that lives in Alaska, that in general, as you live at a more northerly latitude, the temperature tends to go down on average. So in this output below, we have values given for lots of stuff. So part of what I want you to know is how to interpret this stuff. So first of all, you can see that there's the regression line. And then you're asked to find the standard deviation from the regression line. And that's this number down here. And I apologize that my scan's a little grainy, but that's supposed to be a dot in between there. So S is equal to 2.837. And what this describes is the spread about the regression line for a specific latitude. So this is a measure of the spread about the regression line for any specific x, and an x value is a latitude. Latitude. Can't speak and spell. Latitude. And things like your empirical rule would apply to this. You know, you'd have 68% would fall within plus or minus 1 standard deviation of whatever your mean for that latitude was. 95% fall within whatever your mean is plus or minus 2 standard deviations. And what will go into this means box that I left as kind of like a blank box would be what you get when you plug in a specific number into y hat. So y hat with some specific x plugged in. Now in the output, you also see that the value of r squared is given as 91.7%. Write a sentence or two that interprets this value. So this is the proportion of variation in y that's explained by x. So the proportion, so the variation in y explained by x. That's kind of like the general recipe you're going to use to interpret these things. I'm going to start with the x thing. So x is geographic latitude. Geographic latitude, which is my x, explains 91.7% of the variation in y, which is average April temperatures. All right, let's do another example. So example 14.5 gave the regression equation y hat equals 577 minus 3.01x for the relationship between y, which is maximum distance at which a driver can read a highway sign, and x equals driver's age. Notice that the slope is negative, which means that as age goes up, this distance at which you can see a sign goes down, which should make sense. The older you get, the more your sight deteriorates. Okay, first, what is the predicted value of the maximum sign reading distance for a driver who is 21? So y hat is 577 minus 3.01 times 21, which comes out to be 513.79 feet, approximately. So the average 21-year-old can read a sign at a max distance of about 514 feet. I mean, not every 21-year-old, because some 21-year-olds may be slightly blind, as in they have bad eyes, but on average, they can read a sign at a maximum distance of 514 feet. Compute the residual for a 21-year-old driver who can read the sign at a maximum distance of 525 feet. So remember that the residual is equal to y minus y hat. The y value we have is this actual person who can see a sign at 525 feet, minus the average, which is about, we'll just use 514. That comes out to be 11 feet. So this person is about 11 feet above average. The standard deviation from the regression line in this example is approximately 50 feet. So let's use the empirical rule to give an interval that describes the maximum sign reading distance for about 95% of all drivers who are 21 years old. So your empirical rule says you take some value plus or minus 2 times your standard deviation. And the question is, what is that some value? Well, what goes there is the average, and that's what you found in part A. So in this case, it's going to be the y hat and specifically when you've plugged in 21, because we are talking about 21-year-olds. So that y hat that you found is 514 plus or minus 2 times 50. Same thing as 514 plus or minus 100, which as an interval is 414 to 614. And so 95% of all 21-year-olds have a maximum sign reading distance between 414 and 614 feet. So you'd be unusual if you fell outside of that interval, but within that interval, you're kind of within the average, what we'd expect. So would it be unusual for a 21-year-old driver to be able to read the sign from 650 feet? Justify your answer. So I'd say yes. 650 is outside that 95% confidence thing. So you have your bell-shaped thing, and up here is 614, and down here is 414. And that's 95% of all individuals. So yes, this person is strange. So this person falls into where? He falls into the top 2.5% of all 21-year-olds. And so if I ask you a question like this, that's enough of a justification. Give me the right conclusion. Yes, he's unusual. And then tell me where he is. Well, he's in this top 2.5%. And really, he's probably, in the top like 1%. But top 2.5 you can say for sure because he's above the cutoff right there. Okay, so let's refer back to example number 3, in which results are given for the relationship between mean April temperature and geographic latitude. And here is the analysis you might see if you put that data into some statistical software to find that regression line. So we want to talk about how we find all those pieces that give you that R squared. So first of all, what is SSTO? Remember, that stands for sum of squares total. And that's computed by doing the sum of your y's minus your y bar and squaring that. And you see that you have this thing that says SS, and then you have this total column. Well, this number is what would be the sum of squares total. So that is 1746.8. So what that computer has done for you is it's taken every single y value you had, taken away the mean, squared it, and then added them all up. SSE, remember this stands for sum of square errors, and you can think error is how much your regression line is off by. How much your regression line is off by is found by taking your y values that you had minus what you predicted they would be with your regression line and squaring them. And in this case, it's still sum squares, but now we're looking for error, and that's residual error. That's this guy, 144.9. Well, sum of squares residual, or regression, sum of square regression, you can find one of two ways. But remember that this is the sum of the yi hats minus y bar squared. But from the table, sum square regression, that number right there, 1601.9. Note this can also be found by doing SSTO, which was the answer to A, minus SSE, which was the answer to B, will be the same thing. Or you can see that this number plus that number makes this guy. So now using this, let's figure out what that r squared should be. And remember that in the data, r squared was 91.7%. So remember that r squared is equal to SSTO minus SSE all over SSTO. So that's 1746.8 minus 144.9 over 1746.8. And if you input that in a calculator, just put parentheses here, and you get 0.9170, which is about definitely 91.7%, like we found in the previous problem. So when we're talking about regression lines, another question we want to ask is this relationship between two variables actually statistically significant? And the thing you're asking a question about there really is the slope not zero? Because if the slope is zero, a slope of zero means that there's no relationship. And a slope of zero means changes in x don't lead to changes in y. So as long as the slope is not zero, there will be a relationship. And in this case, here is what the null and alternative hypotheses say. So the null hypothesis is that there is no relationship, that true value of the slope is zero. So x and y are not linear related. And h naught is that the slope is not zero. So x and y are linearly related. And the sample statistic is given by the following thing. Sample statistic, which is your estimate of your slope. So estimate of slope from y hat equals b naught plus b1x minus your null value, which is that, well, there's nothing going on, divided by the standard error of that b1 thing. And for reasons I'm not going to go into, this has n minus 2 degrees of freedom. It kind of has to do with the fact that there's an x and a y variable. And if you added more variables, let's say you had two different x's, like using height and waist circumference to predict weight, for example, that'd be n minus 3, but that's not this class. And the standard error is found using this formula, holy moly, and where s is found using that formula. Lots of tedious things here. Often you're just going to be given the components and asked to work with them because it's so tedious. Or given output from software. So the output for a linear regression relating y equals GPA and x equals hours per week spent using the computer for 162 college students is on the companion website. And 11 of these 173 students did not provide complete data. But here is the regression equation for the GPA. Now the question is this slope, like that's a number that's awfully close to zero, but how close to zero do you have to be before you're close enough to be not statistically significant? So, is there a statistically significant relationship between the two variables, and justify your answer using information from the output. Be specific about the null and alternative hypotheses that you're evaluating. So the null hypothesis is that the true slope, beta 1, is equal to 0. So what this is saying is that there's no relationship. Between hours on computer and GPA. and HA is that that slope is not zero, that there is a relationship. Between hours on computer and GPA. Okay, so first we got to figure out what thing you're testing. You see this column that has p-values, but the question is, which thing are they testing? Now you have this constant thing, and you have this computer thing. So what that constant refers to is this, the b sub 0. And you're not testing something about beta sub 0, you're testing something about beta sub 1. So you care about the computer thing, which is the slope. Okay, well for that, you see that you have a p-value of 0.165. That's a p-value corresponding to b1 equals negative 0.00555 is p equals 0.165, which is not less than alpha, which is the typical threshold 0.05. And what this suggests is that you failed to reject H0, and there's insufficient evidence to conclude that there is a relationship between hours spent on a computer and GPA. And last question about this, suppose that P denotes the correlation between the two variables. And what is the p-value for testing this hypothesis? So correlation would be sort of how strong is that relationship between them. And this is actually the same thing as testing the slope. Because this is testing the strength of the relationship. Well, strength and direction. So we also, in this case, have p equals 0.165. So this is just another way of asking the question, is the slope not zero? But the rho value kind of is a scaled value that can account for the fact that sometimes slopes that look like zero might be non-zero because you're working with things that are sort of measured in very small units. Say if you're measuring, like, is the size of a cell changing? Well, those numbers are going to be awfully close to zero because they're little, versus something like this GPA, the slope would have to be much farther from zero to be considered non-zero. Now, a more useful thing, I think, is talking about confidence intervals for slope. So, and because confidence intervals tend to give you an idea of what the spread might be. So I think that they're more useful to help with understanding. So a confidence interval for the true slope is found using the same general principle as we did in chapters 10 and 11. Take your sample statistic plus or minus some multiplier times the standard error. And specifically here, the sample statistic for beta 1 is B1. Our multiplier is a t star value multiplied by the standard error of beta 1. And that t star multiplier is found using a t distribution. So same as in chapter 11. N minus 2 degrees of freedom, think 2 variables, hence the n minus 2, and is such that the probability between negative t star and t star equals the confidence level. So these t curves are also bell-shaped, and the area from negative t star to t star is equal to the confidence level, which is often 95%. Okay, so we're going to refer to the output in example 1 for the simple linear regression that's done to examine the relationship between systolic blood pressure and age. A 95% confidence interval for the population slope B1, beta 1 is 0.7 to 1.1. In the context of this situation, write a sentence that interprets this confidence interval. So first of all, state your confidence level with 95% confidence in the population of men between the ages of 40 and 60. Average blood pressure increases between blank and blank, so between 0.7 millimeters of mercury to 1.1 millimeters of mercury for each 1 year increase in age. And notice that what you kind of do there is you take the slope interpretation. You know, when age goes up by 1, blood pressure goes up by this much. And you just translate that into an interval. It's either between this much per year of an age to that much per year increase of age. All right, in example 14.3, a sample of 43 college men was used to determine the regression equation weight equals negative 318 plus 7 times height. Weights were measured in pounds and heights were measured in inches. The slope of the line is 7, is the proper notation for the slope B1 or beta 1. The proper notation is B1 equals 7 because this regression line is from sample data. It's not the true value for the population. To find that, you'd have to sample every single college man. Okay, the standard error for the slope was given in the output accompanying this example as 1.581. Calculate an approximate 95% confidence interval for the slope of the population. Write a sentence that interprets the interval. Okay, so first of all, we have that the confidence interval is given by B1 plus or minus T star times standard error of B1. And B1 is the slope, which in this case is 7. Plus or minus, we'll figure out T star in a sec. We're told standard error is given as 1.581. Okay. Okay, now to find T star, we have to find the degrees of freedom, which is n minus 2, 43 minus 2, which is 41. That's pretty close to 40, and that's the number that's on our table. And so in this case, we end up with T star is about equal to, let me get my table out, and looking at the degrees of freedom equals 40, we get that T star is about 2.02. And so our confidence interval is 7 plus or minus 2.02, times 1.581. Now 7 minus 2.02 times 1.581 is about, let's just do 2 decimal places. I got 3.806, so 3.81 to 10.19. So that's a 95% confidence interval for our slope. So let's just write a quick interpretation there. With 95% confidence, so think about what that slope means. It's change in y over change in x. So change in y is weight, which is pounds. Change in x is height, which is in inches. So with 95% confidence, if height increases 1 inch, weight increases by between 3.81 pounds and 10.19 pounds. So I'll probably always ask you to interpret your intervals, because it is important you know how to explain what they mean, not just find the numbers. You could also say something like, with 95% confidence, a weight gain of 3.81 pounds to 10.19 pounds occurs with every 1 inch increase in height. There's lots of ways to say that correctly. You can kind of reverse the order, but the kicker is inch increase in height and then this range of increase in weights. So it has been stated that for every 1 inch increase in height, average weight's going to increase by 5 pounds. Does the interval found in Part B explain this statement? Yes or no? Well, yes. And the reason is that 5 is included in the 95% confidence interval. Yes, so because 5 is included in the 95% confidence interval, it is a plausible value for the slope. All right, so that's really it for chapter 14. So hopefully it was a reasonably good review of chapter 3 as well.